Hey folks, welcome back to another video in this series on JAX, and today we will be looking at the JIT functionality. So last time we looked at the PMAP, VMAP functionality. Before that we looked at the autograd, and then the third pillar of JAX is the JIT compilation ability, which is what we will look today. So JIT is a just-in-time compilation system, and what it does is it basically compiles your piece of code during the execution, like right at the execution moment. And so what it does is you give it a function, it'll apply optimizations to that function, make it like hyper optimized, and then run it. So the first time you run the function, it is a bit slow because that is when it's compiling, but the next time you call it, the compilation is done and it'll be much faster. And that's what we will look at today. So we first of all, we import all our libraries, and note we import here jax.jit. Okay, so now I will show you a function with and without compilation. So the first function I have is this, let's call this a flow function, where basically I just apply an operation 100 times, just a sine and cosine of the value of x again and again and again and again. And in the fast function, what I do is I invoke the decorator JIT. I don't need to do the decorator JIT. I can wrap the fast function in jax.jit, so that's the other way, but I prefer using the decorator. Okay, so now we pass in x, like a specific value of x, and then I basically measure the time. So I call the function and I measure the time difference the first time I call the function, and then I also call the function the second time. So first I call my function the first time, then I also time the second function, which is the slow function. First I call the fast function, then I time the slow function, and then I call the fast function again just to check what's the speed difference. Let's see. So the first call takes a lot of time, that's why it is 1.8 seconds, and the slow function, the timing of the slow function is 0.1. So it would seem like JIT didn't do anything, but it spent most of its time compiling. So that's why it took this much time. The second time we call JIT, you can see that it was done in 0.002 seconds. So there was a massive speed up. Let's call it again. So yes, so the first time was an anomaly, but then roughly you will see every time you get like a 10x speed up. So let's run it again. You see there's again a 10x speed up. So just by doing a JIT, you get 10 times performance improvement over regular Python. So it's a no-brainer using this JIT functionality. So the first time Python calls it, what does it do is basically it takes the input value and then it creates the compute graph. We'll talk about how it does it, but then it generates a compute graph and it stores the compute graph in its cache. And every subsequent time you call it, it will just use the compute graph itself. The compute graph is optimized. And again, there could be like low-level optimizations for your particular hardware, but that's all abstracted away from the user. And all you have to do is just use this JIT decorator. Another thing is here, I have a fixed for loop. Note, the for loop is running over like a constant 100 times. So in the compute graph, this would be unrolled, and then this would be unrolled, and then the compute graph of like 100 times of this operation will be saved. The reason for that is the reason why I have it this way rather than an explicit argument is because, well, it will become clear. I'll have some examples, but I'll show you is we don't want to tie the compute graph to an input parameter. because if I had another input n and I was tying this compute to that n, that would mean my compute graph is input dependent, and that would make compiling JIT functions problematic. Sometimes it won't even compile, or even if it does compile, it would be very specific. So for each range, I would have different compute graphs. So that's why I left it as a constant right now. We'll see it in future cells. But yeah, so you have to take in some care when you write functions that will be, or you have to be a bit careful and know how JAX implements this JIT functionality. Okay, so all right, so let's move on. Now, I want to show you an example with two, which is slightly more sensitive to inputs. So let me, so here I have two inputs, rather, yeah. So here I have two inputs, and this function, what it will do is it will return an addition and a multiplication. So the first time I call it, and I will supply it 1, 2 tensors. So you see I supplied a vector for x and a vector for y. So the first time I call it, it will compile. The second time I call it, it will be faster and it will just run on the saved compute graph. However, my claim is the third time I call it, you see, so now the third time I call it with a different shape. So now my inputs are 1, 3 and 1, 3. In this case, my claim is that it will trigger a recompilation. So let's first run it. So it produces outputs as before. So it's not really clear whether recomputation was done or not. However, if I include a print statement, so first let me run it and then I'll tell you what happens. So when I do a print, during the first call, there is a traced array. In the second call, it is not present. In the third call, there is a traced array. So, okay, let me explain now. So when we call the function that is supposed to be JITted, the first time, what JAX does is it creates a dummy input which has the shape as our regular input. So here our input was 2-dimensional. That's why you see it's a float of dimension 2. So it creates a tracer array, so which basically stores the shape of the input and then runs through the compute to generate the compute graph. So for the compute graph, you really don't need the values. All you need is just the shape, right? So it creates the compute graph, and then once the graph is computed, that's why trace was printed. The next time the compute graph is used. So in the next call, we don't even see the print statement because it doesn't even use this function anymore. It uses the compute graph that was generated. However, the next time when we call it with a different shape. There is no compute graph for that particular shape. A compute graph is always tied to the signature of your inputs. If you have different kind of inputs, then it will create different compute graphs. So then you see it creates it goes and searches and sees that it doesn't have a compute graph for shape 3, and that's why it has to recompute the compute graph, and that's why you see traced. And then if we call this function again with shape 1, 3, you won't see this print. So that's if your input shape changes, then JAX will need to recompute the graph. So that's how the JAX optimizations are tied to the shapes of your input. So that's where you have to put in some amount of care. Okay, so let's look at another example. Okay, so this is what I was talking about, pinning my for loop to input. So here I have a case. So let's talk about basically static and dynamic arguments. So here I have an input, which is a for loop. It takes an input x, does some computation, and it does it number of iteration times, which is another input to my function. So in one case, in both cases, so I have this function twice. In the first case, I do a JIT, and in the second function, I specifically tell JIT that it is a static argument. So what is the difference? In this function, number of iterations is not defined to be static, and that means JIT will consider that as a traced input. So what that means is it will create a compute graph with two tracer objects, as we saw, and then when it reaches a for loop, JAX will get confused because the for loop will run number of iteration times, and the number of iteration requires values, right? And if you remember, tracer just has shape. So that's why this will fail. However, in the second case, we explicitly tell JAX to take only the static value and do not trace the number of iterations, and that's why it will succeed. So let's do it. So when I ran, so first I will try the first function, which my guess is will error out. We'll see. And then we'll call the second function. Now, note I'm calling the second function 2 times. So the first time I call it with 5 number of iterations, and then I call it with 3. Now my claim is, and that is what will happen is, for the different values of number of iterations, because we are running for loop different number of times, these will result in 2 separate compute graphs. So if I call it with 5 again, it will be efficient. But then as soon as I change it to 3, because the compute graph changes, because the for loop is pinned to an input, this will trigger a recompilation. So let's first run it. So first, we see that this failed, and the error was tracer integer conversion error because index method was called on traced array with shape, blah, blah. So basically, it failed because it's trying to, so a tracer array doesn't have a value, so it doesn't know what to do here, and that's why it failed. And then and then the other loop where we had static arguments worked. Okay, so, but yeah, remember, if the static argument changes, it will trigger a recompilation. But as I was saying this, I just realized this failed because it required the value. What if I pinned it to the shape? So let's do this. So let me see how does the shape look like. So what I will do is I can pin it to the shape or the length. So what if I do length of number of iterations? So the length is 0, and because it's an integer that I'm passing, and so that, or okay. So I can like, so basically what I'm trying to do here is just passing this will fail, but what if I pass something that is related to the shape, because a traced array still contains the trace information. So if I run it, okay, this failed because we have a type error, but then what I'll do, okay, so this didn't work because and so what if I do shape? And then do this one. Tuple index out of range. Actually, let me see if I can get some combination of this to work. So we are running into the JIT. Okay, let's see. I don't know why this is not going into the loop. So when I call it, so for the first one, I get, so it gets the trace thing. Oh, so for the second thing, it doesn't get the traced item. So what if I just print as is? So I get a traced thing, and if I make it an array, if I make the input an array. Oh, this is just a fun exercise that we're trying to like fool the system. And oh, so sorry, JNP. So now I can use shape. Oh, okay, it worked. So check this out. So when I run it, it worked because now I have pinned it to the shape, and a traced value contains the values of shape, and that's why it worked. This is just like a, I don't know. I mean, now that you know this is how the system works, you can just work around it. So this was just a fun exercise because now we worked with the shape instead of actual value, and that's why it compiled. Okay, now let's look at a different example, and let's look at control flows. Right. So first of all, what if my function has an if-else loop? So here we have two functions, a good conditional and a bad conditional. Now, if and else pattern, which is quite common in Python, do not get compiled properly. Because during compilation, what will happen is, if your if is, even if your if parses, only one of the branches will get compiled, and the other one is not compiled. So it'll always be that you either only have like one branch in your compute graph, and that will lead to error. And that is even if it compiles. So here, this probably won't compile because it requires the value of x. So to write, so then the way around it is to have the if-else in this format where you do, where the conditional is, so you do a gnp.where. So you do the conditional using JAX's comparator. So let's look at this. When we run it, so this one, the good conditional works. It identifies, so there's a tracer that takes in the value, and I get the right result. The bad one fails because we try to compare a tracer with an int, and that's why it fails. So again, you have to become careful when you have conditionals or these branching patterns. Okay, so now another use case. So bit by bit we're looking at slightly advanced use cases. There are tons more, but I'm just giving you like a brief preview of how to use JIT with all these like complexities. So what if you wanted to do compute moving averages, right? And you have you want a window size, and then you want to compute the moving average. So a simple way would have been, so first of all, so the function takes in the data, which is an array, and the window size in which you want to do a moving average. Now, as we've seen before, I want this window size to be a static argument. So here, in both the cases, I specify it as a static argument. In one of the cases, what I do is, so first of all get the total length, then I create an array full of zeros, which is where we will store our result. Then I loop over that array, and then fill that array with the desired results. So this is how you would ideally do. I first compute how much data I have, pre-fill the output with zeros, and then in the output keep on computing the results for each given location. So let's run it. So this works. There is no issue, but it is not optimal because so let me first tell you the other way, and then I will tell you like why this is not optimal. In the other way, what I do is I define a scan function, and what this scan function does is it computes the mean of the slices. So jax.lax.dynamic slice, right? So let's open this up. Okay, so jax.lax.dynamic slice. So basically, let's look at like the functionality. So if I have an array like this, and I do a dynamic slicing, and I specify, so basically I want so let's see what it takes. It takes the array to slice, and it takes the starting indices, and the slice size, and also if you want negative indices. So let's just work with this example. Let's go back, and I create this example, and let me copy that bit here. It's just easy if you like work with an example to give you a sense. Oh. Okay, so I'll also print out x. So my x was a 3x4 array, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And with jax.dynamic slice, I pick up the first element in the row and the first element in the column. So the first element in the row would be this index, and the first element in the column will be this index. So basically, I take, and what is the slice size that I pick? 2x3. So I pick up this slice because my starting pointer is this, and then I pick up 5, 6, 7, a 2x3 slice. If I just wanted 5, 6, 9, 10, then I would do this. So I get 5, 6, 9, 10. So if I wanted a 2x2. So this basically lets me slice my arrays. And here I basically pick up slices of my window size. So basically this is just a fancy JAX native way of slicing my my arrays. And then I'm computing the mean. Now, so this is a function we have defined to do this computation. And then note, I then call it inside jax.lax.scan. So what jax.lax.scan does, so it's like a for loop. So if we look over this, so basically it scans a function over leading array indices while carry along states. So if you think of a moving sum, right? So you keep on adding 2 elements, and then you keep saving the sum in an output array. That is the kind of functionality that jax.lax.scan does. And it will basically output an array. Let me double check. Right, so it outputs a tuple, which is the first thing is a carry operation, like if anything needs to be carried over, and then y is my output array. So basically, it takes a function, and it takes, so what is in it? So basically, if I have a carry to begin with, and then, so this function can be anything that takes in a value a and a value b with carries if needed, and then applies, either adds them or whatever operation you want to produce, and then results in a carry. So in an accumulate, if f is an accumulate function, I am just accumulating 2 things, and then the carry thing would be something that is propagated forward. So this is so you scan through your entire array and keep on applying the operation every time. So let's go back to our implementation. So I call this, I apply the scan function because that is what I want to do to my array. I begin with a 0. My length window is, I pass access as none because I work with the array here itself in the scan function, and the length I specify as n windows. So let me show you like what length is. So how many times do you want to iterate? How many times do we want to do the scan? And I could have written it in a different way where I pass in my data as an x, and then in that case my operation would just be a mean, but then the slicing would be a bit tricky to manage. And then so output would be a carry and the averages, and then basically I just return the averages. So once you see the result, both the Python loop results and the scan results are identical. The reason why we are using this convoluted and complicated manner is it is much better to write any operation, like that includes for loop, if-else statements, slicing and all, in JAX native format. So LAX is basically like a lower level library that JAX has. It is much better to write it in this native JAX format because then optimization can be easily applied. Here, optimization is harder to apply because these are like Python native functionality, and then JAX has to first convert it into JAX, and that might result in some misses and it might not be optimal. And that's why you should always try to write anything that you're applying JIT to make it JAX optimal. So just to show you the timings, let me copy the time. Where was my timing function? Let's wrap both of these calls. So first I will wrap the Python loop, and then I will also time my scan. And then see the time. So Python was 0.08 and the scan was 0.05. So let's run it again, and you can see it's roughly always, the scan is always faster by 20-30%. That's why you want to always try to write things in native JAX format. Okay, so we've seen all of this. How would I use JIT for machine learning workflows? So let me show you like a quick example of that. So here, I define a loss function. My loss function takes in like a dictionary, which is also like a PyTree, which is something that we'll cover later. So this is a new way. So this is the beauty of JAX also, that it can work with PyTrees, which means it can work with different Python containers. So here parameters, so I parameterize, or rather I put my Python or network parameters in a dictionary, which which has the keys, weight, and biases, and then the loss function is just input times whatever the linear regression, the linear function, and then my loss is a mean squared of mean. So that's my mean. Now to get the gradient, I can do a JIT, and so we want the loss with respect to, so we specify the argnums, if you remember from our grad lectures, and we, sorry, I was zoning out. We specify argnums 0 because we want the gradient with respect to parameters, and that's why argnums is 0. So we first define an x and y, our parameters, we first just compute the loss and gradients, and then so this is JITted. And then I could also do a prediction in which I take the parameters and then do an x batch, and then basically I vmap because so this I have a batch of data. So these items are all batched. So that's why I can do a vmap and then to compute the output. So let's just run it. So here you see that the loss is computed, the gradients are computed, and so on. So now what I want to show you is that for a given batch size, so now if I change the batch, so right now I ran it for batch, so my batch was 5. If I change the batch size, the computation will be retraced. So this is the same thing. Every time you, even in machine learning workflows, the batch size is something that keeps changing. So you will have a compute graph that is specific to the batch size. So that's why you want to keep your batch sizes fixed to have the most optimum use of JAX's JIT function. So here we could do the prediction and both the batch predictions and also the loss and training using JAX's JIT functionality. But the key thing is it's tied, the compute graph is tied to the batch size. Okay, so that's that. What if you want to debug a JIT function? What if you wanted to like print something? So let's look at that. So here, if I wanted to print something, if I did just a regular print, what happens is like it gives you a tracer because it's not carrying the value. So to actually print a value, what you have to do is you insert like a print hook, and that is done by jax.debug.print to print out the intermediate values. The alternative is to just disable JIT, but if you want to do debugging on JIT, you have to use this jax.debug.print. On it, you can see I actually get the intermediate value instead of like a tracer value. So here I show you that both the JITted and the non-JITted functions are all close. That means they are numerically equal. So that's that is one thing. There are plenty of other things to think about when you're talking about JIT. Is you cannot use global variables and a host of other things. So you have to be careful when you use JIT. So one thing I always do is run a bunch of tests by comparing JIT functions and without the JIT counterparts to make sure they're all numerically equivalent. And always use JAX native expressions inside a function that needs to be JITted. Yeah, so I think, well, we're 30 minutes into this video. I think this is where I'd like to end about JIT. You can read like way more about all of this on JAX's homepage, but I guess this is all you need to know. Yeah, and the code for this will be on GitHub in the link below. But I will see you next time. Cheers.